Hello, it's Richard Hammock's Calculus 1. We are in part 5 of the course on integration. This is lecture 39C. It's our final installment of lecture 39. In 39A, we talked about initial value problems. In 39B, we defined differentials. In 39C, we're going to put all that together and talk about what are called differential equations. Now, the subject of differential equations is vast. Their whole course is devoted to that. In Calculus 1, we're just going to scratch the surface. We'll talk about the basic definitions and some simple examples. And I hope also to convince you that differential equations are extremely important in applied mathematics. Let's start with the definitions. A differential equation is simply an equation involving a derivative dy dx, or y prime. A solution to a differential equation is not a number, but rather a function, y equals f of x, that makes the equation true. And I'll give you some examples to illustrate this. Think of the equation dy dx equals x squared minus 1. That's an equation that has a derivative in it, so it is a differential equation. A solution to this equation would be a function y equals f of x that makes it true. In other words, if you take this f of x, do its derivative dy dx, that equals x squared minus 1. It's not hard to see what the solutions of this differential equation are. They're all the antiderivatives of x squared minus 1, because for them, their derivatives are x squared minus 1. So our solutions are y equals x cubed over 3 minus x plus c. There are infinitely many functions of this form, one for every value of c. Any such function satisfies dy dx equals x squared minus 1. So those are all of the solutions of this differential equation. And this is typical. Most differential equations are going to have infinitely many solutions, or none at all. Here's another example. Y prime equals x over y squared. It has a derivative y prime in it, so this equation would be a differential equation. A solution would be a function y equals f of x for which y prime equals x over y squared. And maybe this is not as simple as the previous example because the x's and y's seem to be kind of mixed up. But I'm going to pull a solution out of thin air and then convince you that it really is a solution. In fact, I'll give you infinitely many solutions. It turns out that the solutions to this differential equation are all of the functions that have the form y equals 3x squared over 2 plus c all to the power of 1/3. Now let me show you why any function of this form for any c is a solution to this differential equation. We're going to compute y prime for this function and confirm that it really does equal x over y squared. So let's compute y prime. In computing y prime, we've got to use the generalized power rule. We bring down the 1/3 times the 3x squared over 2 plus c to the power of a 1/3 minus 1, which is minus 2/3, then times the derivative of what's inside here, and that's 3x. Now the 3's cancel, and this power of minus 2/3 can come down to the bottom like this. So there's our y prime, but I'm going to change that just slightly. This power of 2/3, let's write that as the 3x squared over 2 plus c to the power of 1/3 and then squared. So these exponents here multiply to give you the 2/3. And look at what we have. We have y prime equals this fraction. There's an x on the top, and on the bottom, there's something squared. And what is squared? The 3x squared over 2 plus c to the 1/3? That's y. So for this y, this expression equals x over y squared. We've just confirmed that y prime equals x over y squared for this function or any function of this form, and that makes such a function a solution of this differential equation. It makes this equation true. Y prime equals x over y squared. So we're going to be concerned with finding solutions of differential equations. That means solving them. Solving a differential equation means finding all of the functions y equals f of x that make it true. In general, solving a differential equation is a very tricky business. It can be extremely difficult. Here we will just look at the simplest kinds of differential equations for which a certain technique is going to work. And that technique is called separation of variables. It doesn't always work for differential equations, but it's great when it does. Every once in a while, you'll have a differential equation that can be solved by, so to speak, separating the variables and then integrating. As an example, think about the differential equation we had on the previous slide, the really transparent one. dy dx equals x squared minus 1. One way to solve this, by separating the variables, would just be to multiply both sides by dx. And then you've got the y's on one side and the x's on the other. You would consider the variables separated here. A dy here and a dx there, right behind a function. You can then integrate both sides. The integral of dy would be the integral of x squared minus 1 dx. And the integral of dy is y, or really it's y plus c, but let's hold off and add that c to the other side. And then the integral of x squared minus 1 is x cubed over 3 minus x plus a constant. So there we have all of our solutions to this differential equation. And they match up precisely with what we had on the previous slide. So we've solved this differential equation by separating the variables and integrating. And as you can see, we get infinitely many solutions. And I'm going to graph those solutions. If you graph x cubed over 3 minus x plus c, the graph really depends on what c is. If c is equal to 0, it'll look something like that. That's one solution. Another solution would be c equals 1, or c equals 2, or the function when c equals 3, and so on. Here's the solution to the differential equation when c is equal to minus 2. Any function of this form, no matter what c is, has a graph that looks like this first graph, just moved up or down c units, and that's a solution to the differential equation. Next example. Let's solve the differential equation y prime equals x over y squared. You'll recognize this equation as the one from several slides ago, where I pulled the solutions out of thin air. And I'll remind you, those solutions were the functions y equals 3x squared over 2 plus c to the power of 1/3. And we confirmed that for these functions, y prime does equal x over y squared. So we know that's a solution. But what I want to show you in this example is how we can use separation of variables to find these solutions. Let's try our technique. If we want to use separation of variables here, we need dy's and dx's, so your first step would be to write that derivative as dy dx. dy dx equals x over y squared. And then you're going to see if you can separate the variables. And in this case, you can just cross multiply, and you get y squared dy equals x dx. So you've now separated the variables, and we can integrate both sides. Now notice it's really important that the variables are separated. If you had a y over here, for instance, this integral would not be something that you could find. But with the variables separated, you can find both of these integrals. The integral of y squared dy is y cubed over 3 plus a constant, but we're going to hold off and add that constant to the other side. And the other side is the integral of x dx, that's x squared over 2, plus some constant. So now we've integrated, but we don't yet have our function y equals f of x because the y is not isolated. We need to solve this equation for y. Let's begin by multiplying both sides by 3. You get y cubed equals 3x squared over 2 plus 3 times c. But that c, we just want to leave that unspecified. So rather than calling it 3 times c, just call it c. It's just a constant. And we've almost got the y isolated, but it's cubed here. So in our final step, we take the cube root of both sides. We'd raise both sides to the power of 1/3, and doing so gives us what we have down here, y equals 3x squared over 2 plus c to the power of 1/3. So we've just used separation of variables to find our solutions. We've got the solutions here, but also I want to go ahead and graph some of these solutions just to give you a feel for what they look like. If c were equal to 0, we'd have y equals 3x squared over 2 to the power of 1/3. And you've seen that function before. Our function's very similar to it. It has a cusp right there at x equals 0 where the derivative is not defined. But if you add a 1, make c equals 1, you get a slightly different function, and it's going to look like this. If c were equal to 8, that function graphed would look something like this. If c were equal to 27, the graph of that function looks like this. You could also have negative values of c. Remember, we're taking the cube root here. You can take the cube root of negative numbers, so that's not a problem. If c were negative 6, the graph gets kind of interesting. It comes down like this when this c is minus 6. So that's one of our solutions, one of infinitely many solutions, one of infinitely many functions of this form that satisfy this differential equation. If c were equal to minus 25, you get that function. And if c is equal to minus 56, the graph looks something like this. So you can see that these functions are filling up the plane. And they're not one graph moved up or down c units, because here that c is just not tacked onto the end. It's sort of embedded in the function itself. So you wouldn't expect to get all the same shape. And in fact, you're not. So we have a whole family of solutions, and we've just used separation of variables to find them. We've done this example, but I want to continue it just slightly with a sort of fine-tune the problem. We have infinitely many solutions. Let's see if we can find the solution that passes through the point 2 minus 5. Out of all of these solutions, which function passes through that point? Well, 2 minus 5 is about right there on the plane. So we are looking for the value of c for which the solution passes right through that point. So basically, we just need to find out what c is to get a function going through that point. How would we do that? Well, if we plugged in 2 to the function, we'd get minus 5. So plugging in 2 for x would give you a minus 5 there. So let's write that down. We get minus 5 equals 3 times 2 squared over 2 plus c to the power of 1/3. Now here c is the only unknown, so we can start to solve for it. Simplifying 3 times 2 squared over 2, that's 6. So we get this equation. And we want to isolate the c, so we better cube both sides to get rid of that cube root. Doing so, we get negative 125 equals 6 plus c, and finally, c is equal to minus 131. So we found c. Now, of course, that's not our solution because we're looking for a function. It would be this function with c equals minus 131. So answer, y equals 3x squared over 2 minus 131 to the power of 1/3. For that value of c, our solution goes right through that point. So in this continuation of our example, we had, so to speak, an initial condition that gave us an exact function, a value for C. In our next example, we're going to set up and solve a differential equation that gives the shape of a cable on a suspension bridge. Like, for instance, London's Tower Bridge, as illustrated here. What's happening is that you have a road or platform that's horizontal, and the weight of that platform is distributed evenly horizontally. It might be something like, I don't know, 1,000 kilograms per meter or something like that, distributed evenly throughout this stretch. And that platform is being supported by a cable that runs between two towers with vertical cables connected to it. And what we want to do in this problem is to show that the shape of this supporting cable, this suspended cable, is actually a parabola. It has the form of y equals ax squared plus c, where a and c are appropriate constants. So we want to show that a cable supporting a load distributed horizontally has the form of a parabola. Our solution will use a little bit of physics, and if you're not familiar with that, you can ignore this example and you'll be fine. But let's see if we can figure this out. Look at this situation and put it on a graph. Let's say that our cable is put on the graph so that its lowest point is right there at the origin. And we don't know what shape this cable takes, so let's just call it y equals f of x. And the idea is we want to figure out what f of x is. Let's say that this end is attached securely to a tower, and the other end over here is attached to a tower, and we're really going to pay attention starting at this origin point right there where the slope to y equals f of x is horizontal. And for that segment of the cable illustrated here, we have vertical cables running down to, you might think of them as evenly distributed weights, as illustrated here, connected to the cable, and they pull it into a certain shape, y equals f of x, that we want to find. So if you think about what's going on here, at this point right there, that cable is pulling the other side of the cable with some force. The connecting cable here has to pull with some force F that's horizontal. Let's just call that force F. Now we want to work out f of x. So imagine this whole system is in balance now with this one force F pulling the cable backwards and everything is still. And imagine you go to the x-axis right here, maybe an x that's right there, and you go up to the cable and imagine cutting that cable right there at x. And what you're going to do is you're going to hold it together. Your left hand is holding the left side of the cable, and your right hand is holding the right cable together. And so you've got to pull those two together with a certain force. And right here, your left hand is pulling this cable with the force that's tangent to the cable. Some force that's denoted as T, T for tangent. And this whole system is in balance. Let's think about this tangent force T. Everything is in balance, so the horizontal component has to balance out the horizontal component F here. This has to be a horizontal component of minus F, F in the other direction. And then there's also a vertical component to T. We'll denote it in green, and think about what that is. That's the upward force the upward component of t, and that has to counterbalance the weights that are pulling this whole system down. And so what is the weight of these green weights here? Well, they're distributed horizontally. You've got a distance of x, and let's say that the weights are a constant of w kilograms per unit of x. So we have x units here, so the total weight would be w times x. So this green force is wx. Now, we are looking for the function f of x. Notice we're getting some information about its tangent, in other words, about its derivative. If you think about this x right here and going up, and this could be any x, let's take this one, go up to this point, this red force vector is tangent to the graph of f of x. So its slope is equal to f prime of x. And notice that we have rise over run here. So f prime of x is going to be rise, wx, divided by run, which is the magnitude of negative f. Let's write that down. F prime, which is dy dx, equals rise, wx, over run, the magnitude of minus f. And remember, w is a constant. It's the weight per distance unit of the platform. And f is a constant as well. The system is in balance. F is this constant force here. So w and the magnitude of f are constants. So this equation is just dy dx equals some constant k times x. And there we have a differential equation. It's an equation about a derivative, dy dx equals k times x, and we're looking for this function y equals f of x. So solving this differential equation will tell us the shape of this suspension bridge. We can solve it by separation of variables. In fact, it's really easy. Multiply both sides by dx, integrate both sides, and the integral of dy is y. The integral of kx dx is kx squared over 2 plus c. And that k over 2, let's just call that a. So there is our equation for this cable. It's y equals a x squared plus c, where a is some constant, as is c. And that solves the problem. It shows that the shape of a suspension bridge in balance is a parabola, a squared function. And we use differential equations to find that. We've just shown that a suspension bridge has the shape of a parabola. And this is in the situation where the load is distributed horizontally, like the cable is supporting a platform or a road. It's a very different thing if you had a freely hanging cable that's not supporting anything except itself, as if it's a string of beads. We're not going to do it here, but you can set up and solve a differential equation to show that this shape is y equals a constant times e to the x plus e to the minus x plus b. It's not a parabola, it's a very different curve, and in fact it has a name. It's called a catenary. Catenaries have been used a lot in architecture. The architect Eero Saarinen used this shape for the St. Louis Arch and also for Dulles Airport. And the Catalonian architect Gaudi used it extensively in his work. It's a very beautiful shape. If you find this kind of thing interesting, you should definitely take a course in differential equations. It's a huge topic, and we're barely scratching the surface in this brief lecture. That's it for today. Coming up next in lecture 40, we're going to start looking at something that looks like it's a whole different problem, but it's actually not. We're going to begin to investigate area under the graph of a function. And the surprising thing is that it turns out that that is related to antiderivatives. That's coming up, and I'll see you then. And goodbye.